So action potential. What is an action potential? It's basically when there's a rapid change in voltage or electrical potential across a membrane along a nerve cell. It's propagated by the movement of sodium ions through voltage-gated sodium channels. It's written there, and it causes depolarization in areas around it, and does so by opening the other voltage-gated or inducing the opening of other voltage-gated sodium channels. So originally, there is a steep concentration of sodium ions that's present outside of the neurons. So you can kind of like imagine there's, this is the neuron. So this is like outside, out, this is in, and this is out. So initially outside, there's going to be a lot of sodium ions. So as the voltage-gated sodium channels open, the sodium ions going to rapidly enter the neuron, and this will make the inside of the membrane less negative and more positive. So initially, the inside of the membrane is relatively more negative, and the outside is relatively more positive. So as sodium ions, Na+, moves inside, this is going to make the inside less negative. So when this voltage on the inside reaches a threshold of, in the diagram it shows at around negative 55 millivolts, is going to cause depolarization, which is basically an increase in the voltage to some positive voltage instead of like the original negative 70 millivolts during the resting potential. So then repolarization occurs when the voltage-gated potassium channels open, and the potassium ions will exit the neuron rapidly because there is a higher concentration of potassium ions inside than outside of the neuron. So that's like the complete opposite of like the sodium ions. So it's trying to get out. So the efflux of these potassium ions will cause the voltage to drop and return the membrane potential to a more negative level. So originally it was like already negative, it was already at like negative 7 degrees, but now it returns it to a really like even more negative membrane potential. So this during this period, the neuron will enter a refractory period where the resting potential has to be like restored before the neuron can fire again. And during this period, the sodium-potassium pump is involved to pump 3 sodium ions out of the cell and 2 potassium ions into the cell, which increases the membrane potential, and that causes it to go back to the like whatever it was like during the resting potential. So another thing to mention about the neurons or like the axon is that there is the presence of myelin sheaths, and this basically speeds up the conduction of the action potential by what's called saltatory conduction. So I'll write that there. Saltatory conduction. And this is because of the myelin sheaths. And this feature makes the electrical impulse conduction way faster than if it were like continuous depolarization that would have been present if the neuron had no myelin sheaths. So if it would be easier to visualize it this way. So let's say this is an axon, and here we have to jump from da 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 for depolarization to occur. However, when there's myelin sheaths, so ignore that, there's myelin sheaths here, it's only going to jump from node to node like this. So it's going to be way faster. So yeah, that's everything I have to say for in this video, but also just note that here it also mentioned that if the voltage doesn't reach the threshold, then there isn't going to be depolarization, or thus the action potential, and these are called failed initiations. So it's really essential to reach the threshold voltage in order for all of this to happen. Best of luck and bye.